let's have this problem from James Stewart's Calculus, the Early Transcendentals, another very good book on calculus. So a trough is 10 feet long, and its ends have the shape of isosceles triangles, meaning two of the sides are equal, that are 3 feet across the top and a height of 1 foot. If the trough is being filled with water at the rate of 12 cubic feet per minute, we want to find how fast is the water level rising when the water is 6 inches deep. All right, this is a very interesting problem. Okay, let's draw a figure first. It looks very complicated because of so many geometric terms. So it really helps if we do an accurate and nice looking figure at the start. I mean, figures are also investments. They're guides to thinking. So let's draw a nice looking isosceles triangle here. It's not nice looking, it's not isosceles in this case. Let's redraw it. Okay, this one is better. Let's just copy paste it. I would rather use the ruler, but let's see where freehand will take us. Okay, pretty decent, I guess. And let's fill it with water, maybe up to here. Let's use the highlighter tool. Of course, when we're in a high stakes exam, it probably might not be the best area to shade it, but we can think while shading, I guess. Okay, so 10 feet long. Again, this 10 feet over here is a constant. It's not a known value of a variable. Rather, it's a constant. It's always 10 feet long. The trough is always 10 feet long. So this is always 10 feet. So 3 feet across the top, that means this thing is 3 feet and have a height of 1 foot. So this is 1 foot. All right, nicely labeled. Okay. So as not to clutter the figure, perhaps it would be better if we just have the 10 feet over here. It's the same thing after all, just so the figure is not cluttered. Aesthetics only. Okay, let's delete this. Okay, better. So this is the rate, so it's not part of the figure. 6 inches deep, is this part of the figure? Let's look at the keyword when. So that means it is a known value of a variable as opposed to a constant. So not really, we don't want this to be part of the figure. It's not constant after all. But it does tell us that we're interested in the water level, the height of the water level in particular, this over here. Let's call it H for height. There, and we have a complete figure for our problem. I think it would be nice if we move this just a little bit of points. Okay, so let's begin with our variables. What are the variables for this specific problem? T is always the variable of interest. It pertains to our time after all. Excuse me. H is the water level at time T. And what's the other variable? 12 cubic feet per minute. That implies that we're also interested in V. That's the volume of the water at time T. Again, just to emphasize, we're talking about the volume of the water here, not the volume of the prism per se. It's the volume of the water. H is the water level also. So now that we have our variables, our next step is to decipher what are the given in this problem. So we skip 10, we skip 3, we skip 1. They're constants after all. Being filled with water at the rate of 12 cubic feet per minute. So that means dV, dt, that's the volume, is equal to 12. And what are we required to find? How fast is the water level rising? So that's a dH dt when the water is 6 inches deep. This one 6 inches deep. So that means when H is equal to 6. Oops, not really. Inches. So that means it's not in feet. The units are not in sync with each other. So what's the conversion from inches to feet? The conversion is 1 foot is equal to 12 inches. The foot-long ruler or the foot-long hot back during face-to-face classes. So H here, since it's 6 inches, 6 inches would be half a foot. So H would be 1. Again, it's from the conversion between inches to feet. All right. Let's erase this thing so that it wouldn't bother us while we're solving. Okay, that's a remnant from the previous problem. Let's also erase this. Let's find the relationship between the variables. Now, the volume of the water at time t, this blue thing over here, is a triangular prism. It's a Toblerone. So the volume of a triangular prism, or of any prism for that matter, is the area of the base times the height. I encourage our viewers over here to try to think about why this is the case. So it's the area of the base times the height of the prism. Let's be careful here. Height of the prism, and the height of the prism is defined as the distance between the two bases of the prism. So in this problem, the height of the prism is actually 10. We might have to tilt our head a little bit, or let's itayo natin yung triangular prism or yung Toblerone form. So that's the height of the prism, the distance between the bases. So that's the 10 over in this problem. Not the 1, it's the prism itself. 1 over here is the height of the base of the prism. The height of the prism is 10. Height of the prism is 10. So this is the area of the base times 10. Now, what's the area of the base? Again, just to reiterate, because this might be a little bit confusing. We are talking about this for the base. This is the base over here. This is the base over here. So the area of the base, it's a triangle. So it's 1/2 base times height. Okay. Might be useful if we have this as a variable d. So 1/2 area of the base, again, that's 1/2 BH multiplied by 10. Again, the figure over here is the base. The base that we're talking about is this base over here, the blue one. Let's draw it here. So like that. This is the B, and this is the H. Okay. But then we introduced another variable, which is another complication. In mathematics, well, more variables spells more doom. So is there a way for us to get rid of one of the variables over here? Meanwhile, I'll get rid of this. It doesn't interfere with our work. Okay. Perhaps there is. And what's that way? Let's go back to the figure over here. Let me redraw this figure. Let's focus on this one. I'll draw the figure here. That's the blue one, and then this one. Okay. Again, this is our B, and this one is our H. We're talking about this over here. This is 3, and this is 1. Do you see where we are leading here? Look at this triangle and look at the big triangle. The key concept that should click for this problem is the notion of similar triangles. The big triangle, the big yellow triangle, is similar to that small blue triangle. So the yellow triangle is similar, the symbol for similarity, to the blue triangle. That means the sides are in proportion. What does that mean? The base of the yellow triangle is 3, the height is 1. The base of the blue triangle is B, the height is H. So the proportions, they form a proportion, the ratios are equal. So we cross multiply this, 3H is equal to B. And here, we have a nice equation that we can use now to simplify this over here. How are we going to simplify it? Okay. So 1/2. What's our B? Our B is 3H. B is 3H times 1, 5. 5 times 3 is 15. 15h squared. So now we have a formula that relates the volumes together. So V equals 15h squared. Okay. So now we can perform substitution over here. So V is equal to 15h squared. Oh, before we perform substitution, we first look for the derivative. So that's with respect to time, dv dt is equal to 15 h squared to h multiplied with h dt, because we're doing implicit differentiation here. So it's equal to 30h multiplied by dh dt. So that's our dv dt. And we plug in the values into our our given over here. dv dt is 12, so 12. We want to find dh dt when h is equal to 1/2. So let's do it. 30, h is equal to 1/2. H is equal to 1/2, so let's have it as 1/2 multiplied by dh dt. Let's just focus on this part of the whiteboard for now. Let's simplify this thing over here. 12 is equal to 15 multiplied by dh dt. So that means dh dt is equal to 12 over 15. A little bit particular with how equations are written, so let's have the dh dt 12 over 15. That is equal to, simplify, divide by 3, divide by 3, 4/5. And the units, we're looking at feet in this problem. So feet per minute. This is feet. It's the water level after all per minute. So this is the final answer to this problem over here. Okay. So let's take a minute or two to appreciate the problem that we have here. So let's have a recap. First, we drew the figure. We have our figure over here. We identified our variables, namely T, time, H for the water level at time T, followed by V, the volume of the water at time T. We listed our given. We only have one given actually. The dv dt is equal to 12. What are we required to find? dh dt when h is equal to 1/2 or 6 inches. We did the relationship. So the volume is area of the base. This is the volume of the water at time t. The area of the base times height of the prism. Area of the base times 10. So 1/2 pH times 10. B is the area. The B rather is the base. This one. Portion with water. So because we want to get rid of the variables, we want to get rid of at least one of the variables here, we need to find a way to get rid of B, for instance, and we do it using similar triangles. So notice that the yellow one, the yellow part, which is this one, the yellow triangle is similar to the blue triangle over here. So using triangle similarity, we get that base over height 3 over 1 is equal to base over height 3 over h. That means 3h is equal to b. We plug it into this equation over here. So 1/2 times 3h times h times 10. We simplify to get 15h squared. So now we have a nice equation that relates our variables v and h. We perform implicit differentiation. V equals 15h squared to get that dv dt is equal to 30h multiplied by dh dt. We plug in the equations from here. dv dt is 12. We want the dh dt when h is equal to 12. So, sorry, when h is equal to 1/2. So h is equal to 1/2. So 12 equals 30 times 1/2 times dh dt. So doing some algebraic manipulations, we get that dh dt is 12 over 15, or simplifying, that's 4/5 feet per minute. So that is this trough problem over here. So for our final problem in this video, we are going to take a look at a more challenging problem that already involves trigonometry. Alright, for our final problem, we are going to take a look at another problem from James Stewart's Calculus, the Early Transcendentals. This is the lighthouse problem. A variation of this one can also be found in Lighthold, but we're doing Stewart's version here. So a lighthouse is located on a small island 3 kilometers away from the nearest point P on a straight shoreline, and its light makes 4 revolutions per minute. How fast is the beam of light moving along the shoreline when it is 1 kilometer from P? This one is a bit on the navigation side. So interesting how related rates ramify to different areas. Very interdisciplinary in this sense. So let's sketch the problem first. A lighthouse is located on a small island 3 kilometers away from the nearest point P on a straight shoreline. What does that mean? That means we have a straight shoreline over here. We have a point P. Nearest point P. The nearest distance is always the distance that forms a straight line. Again, the nearest distance, the shortest distance, is always that of a straight line. So if I draw a straight line over here, I find my lighthouse over here. So this is my lighthouse. I would have loved to draw a lighthouse, but my drawing skills are inadequate for this. And from the lighthouse, it emits a beam of light. Okay. So let's say the beam of light is this. There. Okay, that's the beam of light. The beam. So it's 3 kilometers away. In this problem, we only have one constant. That's 3 kilometers. Again, this 1 kilometer, as we have mentioned a while ago, when is the keyword that tells us it's a known value as opposed to a constant. It's a known value of a variable. But it also gives us an idea that we are interested in how fast is the beam of light moving along the shore, and it is 1 kilometer away from P. So that means we're interested in this distance over here, this horizontal distance over here, that horizontal distance x. Okay. Let's try to see. Variables. T is always our variable of interest. It's the time. And what is x over here? X is the distance of the light beam from P at time t. But wait, we're lacking another variable. We have t, we have x, but sun related is x. What variable is x related? This one requires a little bit of creativity. We're doing revolutions per minute, 4 revolutions per minute. Very suspicious. When we're talking about revolutions, what is related to revolutions? If you're thinking angles, then that is precisely correct. We're interested also in this theta over here. So this theta is that angle measured the standard position at time t. So for simplicity, let's just call it angle at time t. So this is theta over here. This will allow us to make use of the fact that there are 4 revolutions per minute. Okay, so now that we have all our variables set up, it's time to set up the given as well. 4 revolutions per minute. Let's take a minute to ponder about this. It's related to theta, but we know it's also a rate because it's per minute, so it's a derivative, it's a rate of change. But then, what exactly does 4 revolutions per minute? How does it translate in terms of theta? Thinking about it, a revolution is 360 degrees. 360 degrees in radians stands for 2 pi, the circumference of the unit circle. That's 2 pi, 60 degrees. Everything is in radians. Okay, so 4 revolutions actually translates to 4 multiplied by 2 pi, because again, 1 revolution, 360 degrees, 2 pi radians, 8 pi per minute. So that means the theta dt is equal to 8 pi. This is one of the early insights that must be gleaned in order to solve this problem. Again, the theta dt, 4 revolutions per minute, translates to 8 pi because 1 revolution is equal to 2 pi radians. Radians is a dimensionless unit. A radian is a dimensionless unit, so no need for dimensions. 8 pi. So that's 8 pi radians. But radians is dimensionless, so that's why we just have 8 pi over here. But just to be more explicit, let's have it as 8 pi radians per minute. Okay. Can we extract some other information from the problem? For now, it seems that this one is the only thing that can help us. So now let's proceed to the RTF, or what's required to find. We want to find how fast is the bee moving along the shoreline. How fast is the bee moving? So that's a dx dt along the shoreline. That's x, the distance of the light beam from P at time t, which is the shoreline distance. So the dx dt when x is equal to 1, because we're talking about 1 kilometer. Okay. Now, time for the relationship. We have theta, and we have side lengths of a triangle. And yes, this is a right triangle. What seems to come into mind? It's trigonometry. In particular, we have opposite over adjacent with respect to theta. So opposite over adjacent. SOHCAHTOA. So that means we are using tangent. So tangent theta is equal to x over 3. Or we say cross multiplication, x is equal to 3 tan theta. We perform implicit differentiation in this problem with respect to time. Okay. The derivative of tangent is secant squared. Again, the derivative of tangent is secant squared. So over here. Okay, so far so good. Let's see, can we already plug things into the equation? Dx dt, we're looking for dx dt. Okay. We know that this one, let's use the blue marker, is equal to 8 pi. So 3 secant squared theta multiplied by 8 pi. But then, we don't really know what theta is, or we don't know what secant squared theta is, much more 3 secant squared theta. So we first need to find a way in order to resolve this. The question is how? How are we going to resolve this over here? Let's look back at the figure. Okay, and ponder on this. When x is equal to 1, anong itsura ng figure? What does the figure look like? When x is equal to 1, let's just extract the right triangle. 3, and then this one will be 1 when x is equal to 1. Again, we're taking a snapshot at a point in time. That is the point in time when x is equal to 1, which is the one that we're interested in. Okay, this is still our theta over here. Can we solve for theta directly? Arctangent perhaps of 1/3 that's not really a very good idea because we don't have a calculator with us and we want to find the exact value instead of an approximation. So, okay, we need to look for a different approach. Well, do I need to solve for theta directly? Perhaps I don't need to because after all, what I need is secant squared theta. So that means I just need to solve for secant theta. And what's secant theta again? Secant theta is the reciprocal of cosine. So 1 over cosine, that's hypotenuse over adjacent. In this problem, the adjacent is theta, so the adjacent is this one. Yung katabi ng theta, that's 3. What's the hypotenuse here? To solve for the hypotenuse, we can use Pythagorean theorem. So by Pythagorean theorem, the hypotenuse, which is this one, is square root of 3 squared plus 1 squared. But this is square root of 10. The square root of 10 over here. Now we have secant data. And now we can plug it into this equation over here. Again, this is 3. This is a secant squared theta. So square root of 10 over 3 is secant theta. So we have to square it in order to get secant squared theta. Then we multiply it by 8 pi. And we proceed with algebra. So yellow marker for consistency. This is 3. Square root of 10 over 3, the whole thing raised to 3 is 10 over 9 multiplied by 8 pi. Can we cancel some things here? 1, 3. Okay. And no more. So this is an 80 pi over 3. What is the unit? How fast is the beam of light moving? So we're talking about kilometers. And the time unit is per minute. So this is 85 over 3 kilometers per minute. So that is how we approach this problem, which involves trigonometry. Okay, so let's take a minute to appreciate this problem over here and look at the bigger picture. So the solution might seem shorter compared to the other problem, but arguably this is harder because of the presence of trigonometry, which requires a bit more insight compared to triangle similarity. So again, this is from James Stewart's textbook. So we sketch the figure. We deliberately have this figure over here. Again, the shortest distance is always the distance that travels of a straight line. So this one over here, this is 3 kilometers away from the nearest point P. Then the dashed line is the beam. X is the distance from P to the beam, to where the beam hits the shoreline. The straight shoreline is the horizontal line. And then where did we get the inspiration to have theta? The inspiration for this theta is because we are dealing with revolutions. So this is the light bulb moment, revolutions. So perhaps getting the angle is a good idea. So translating 4 revolutions per minute, a revolution is 2 pi radians, so that will be 8 pi radians per minute. That's the derivative of theta with respect to t. We want to find dx dt when x is equal to 1. We use trigonometry in order to relate the sides and the angles. Particularly, we use tangent because we know the opposite and the adjacent. So x equals 3 tan theta, dx dt over here. Take the derivative. Derivative of tangent is secant squared. But how do we get secant squared theta? We look at a snapshot of the figure when x is equal to 1. Secant is hypotenuse over adjacent, so it's square root of 10 all over 3. As we have seen here, we square it since we want secant squared, that's 10 over 9. Then perform the usual arithmetic and we get 80 pi over 3 kilometers per minute. And that is how we solve this last problem for the related rates video lecture. So a panoramic look at the problems that we've solved so far. 1 trigonometry, 1 3D geometry that boils down to similar triangles. The classic leaning ladder problem involving Pythagorean, and the 2 more problem which involves relating the volume of a sphere to its radius. So this concludes the video lecture for today. On behalf of the Peer Tutor Society, we would like to thank all our tutors who participated in this video lecture, who volunteered to teach various topics that are covered in first year and second year computer studies and mathematics related courses, and also to the Salle Computer Society for partnering with us for this project. Thank you and have a good day.